So after introducing matrices as linear functions between linear vector spaces, Euclidean linear vector spaces, we are going to now talk about the square matrices of size 2 and size 3. We're going to talk about the notation and the summation convention that's usually used in solid mechanics. Then we're going to talk about the determinant of a matrix as a measure of its invertibility, and what the functions of what other roles the determinant plays. And then finally we're going to introduce the transpose of a matrix, the inverse of a matrix, and the eigenvalue and the eigenvectors. So in an Euclidean vector space, in particular in R3, once we choose an orthonormal basis set, let B equals to E1, E2, and E3 be the orthonormal basis set, then the following holds, or the following hold. We know that E1 dot E1, which is equal to norm E1 squared. Again, this is an identity that's only true for Euclidean vector spaces. And we know because B is an orthonormal basis set, then all these vectors have norm 1, which means this is also equal to E2 dot E2, which is equal to norm E2 squared, which is equal to E3 dot E3, which is equal to norm E3 squared. All these are equal to 1. We also know that E1 dot E2, the dot product between all the three vectors, since they are orthogonal to each other, then the dot product between each two vectors that are not equal to each other is equal to 0. So we can summarize those two big equations into a very small, or into one equation, by introducing something called the Kronecker Delta. The Kronecker Delta, with the symbol delta ij, is equal to ei dot ej, where ei and ej belong to the orthonormal basis set B, which actually will have either of two values, either 1 or 0. If I is equal to j, then the value is 1. If I is not equal to j, then the value is 0. We also know that for every x in R3, there exists n unique components in R where I is equal to 1, 2, and 3. So we have 3 components such that x can be written uniquely as x1 E1 plus x2 E2 plus x3 E3. which we can write as the sum from I equal 1 to 3 xi ei. Now, in continuum mechanics, the researchers or mathematicians working in continuum mechanics have adopted a convention which is called the summation convention, or the Einstein Summation Convention, by which we can, once we have xi multiplied by ei, we can just write it xi ei, and when the index I is repeated, then summation is implied. Now, throughout the course, I'm always going to make it clear whether summation is implied or not, whether I'm using this convention or not. Another convention that's used is the alternator, epsilon I j k, which, depending on the values of I and j and k, can be equal to 1, can be equal to -1, or can be equal to 0. It's equal to 1 when I, j, and k are in cyclic order. Equal to -1 when I, j, and k are in non-cyclic order. It's equal to 0 otherwise. So for example, and of course here I, j, k have values of 1, 2, or 3. So what the above means is epsilon 1, 2, 3, so these are in cyclic order, is equal to epsilon 2, 3, 1 is equal to epsilon 3, 1, 2 is equal to 1. And now epsilon 2, 1, 3 is equal to epsilon 3, 2, 1 is equal to epsilon 1, 3, 2 is equal to -1. These are non-cyclic order. So here it's 1, 2, 3, that's a cyclic order. Then 2, 3, and then start again, that's a cyclic order. 3, and then start again, 1, 2, that's a cyclic order. So that's why it gets a value of 1. Here, the order is the opposite, and so it gets a value of -1. Otherwise, so if you have, for example, 2, 2, 3, or 3, 3, 2, or anything else that does not follow these two, anything else will be equal to 0. So why would I introduce such notation or such a strange quantity, the alternator, which can either be can have 1, -1, or 0, depending on the values of I, j, and k? The reason why I would introduce something like this is to, if I have u, v, and w in R3, three-dimensional vectors, then the alternator allows me to write the cross or the triple product. Remember, triple product from the first part of the linear algebra. The triple product, which is equal to u1 v2 w3 minus u1 v3 w2 plus, I could simply write it using the alternator in this form, epsilon I j n k u I v j w k, and of course the summation is implied I and j and k from 1 to 3, which is basically using the summation convention I j k epsilon I j k u I v j w k. When I see I repeated, that means there's an implicit summation sign. When I see j repeated, there's an implicit summation sign, and so on. So, in the above, we have shown the Kronecker Delta, the alternator, and the summation convention. For repeated indices. So let's look at examples. The first example is what happens when I take the dot product between a vector u in R3 when b equal to ei is the orthonormal basis set in R3, then when I take the dot product of u with ei, this is equal to the sum I equal 1 to 3 ui e, or let's I'm gonna have to put another index here because I already exists. So from j equal 1 to 3 uj ej dot ei, which allows me to write it like this: the sum from j equal 1 to 3, or using the summation convention, I don't need to write the sum sign. I'm just going to write uj ej dot ei. But I know that ej dot ei is equal to the Kronecker delta, and the Kronecker delta tells me that that this quantity will give me 1 only the case when j is equal to I, which means this quantity will be non-zero only when j is equal to I, so this will give me ui. Now let's look at ei dot m j. If m is equal to the matrix m11, m12, m13, then me1 is equal to m11, m12, m13, e1 is equal to 1, 0, 0, which will be equal to m11, m21, m31. If I take me1, if I take the dot product with, for example, e2, this will be equal to m2, 1. And you can try this for all the other possibilities to find that ei dot ej will give you the component on the ith row and the jth column of the matrix M. So there are a few other examples that you should also check using the summation convention. The next thing that we want to discuss is the determinant of a matrix, in particular the determinant of a matrix for two-dimensional matrices and three-dimensional matrices. A matrix that's a 2 by 2 matrix and a matrix that's a 3 by 3 matrix. And we're going to introduce the determinant just by the definition, or as it's defined for these matrices, and then try to understand what the definition implies. So the determinant of a 2 by 2 matrix, let M be this matrix that's made out of two vectors, vector A, which has components A1 and A2, and vector B, which has components B1 and B2. And the determinant of the matrix M is defined like this: A1 B2 minus A2 multiplied by A1. And the objective of the next is to show that this determinant is 0 if and only if, which means that those two arguments are equivalent. The determinant is 0, that means that the matrix is not invertible. Now I'm going to recall in the last part of these lectures that we showed that the matrix is not invertible if the two vectors, that horizontal vectors that form this matrix, are linearly dependent. So this is equivalent to the two vectors forming the matrix are linearly dependent. They are multiples of each other. If these two vectors are multiple of each other, then M is not invertible, and then the determinant of M is 0. Or if the determinant of M is 0, that means M is not invertible. It also means that the two vectors forming the matrix are linearly dependent. And let's show it. If A is equal to alpha B, which means if A1, A2 is equal to alpha, it's a multiple of B1, B2, which means A1 equal alpha B1, A2 equal to alpha B2. What does this mean? It means that the determinant of M will equal to A1 instead of A1, so A1 B2 minus A2 B1. I'm going to replace A1 with alpha B1, alpha B1 B2, minus, instead of A2, I'm going to replace it with alpha B2, and indeed it's equal to 0. So if the two vectors are linear function of each other, this leads to the determinant equal to 0. And also, if the determinant is 0, you're going to find that A has to be equal to a linear function of B. And therefore, the matrix if the determinant Therefore, if the determinant of M equal 0, this is equivalent to A and B are linearly dependent, which from the previous part means that M cannot be inverted. Now, what does the determinant do? So the determinant indicates whether the matrix is invertible or not. It also has another function, which is, it tells me something about how areas transform from one vector space to another vector space. Especially in, we're talking here about matrices that transfer from one, from R2 to R2. If I have a vector, the basis vector E1 and the basis vector E2, and if my matrix is such that M is made out of A1, A2, B1, B2, then if I multiply M by E1, which is 1, 0, I'm going to get A1, B1, and I'm going to call this vector x1. So when I apply the matrix M to E1, I get the vector x1, and when I multiply the matrix M by E2, similarly I get A2, B2, which is vector x2. The determinant of M is in fact the area shown in the in between the vectors x1 and x2. So this area is equal to the determinant of M is equal to A1 B2 minus A2 B1. And if you have 5 minutes, you need to verify that I'm not lying to you, and that indeed this area has value of A1 B2 minus A2 B1, given that the coordinates of this point is A1 B1 and the coordinates of this point is A2 B1. You need to verify that it's true that this area is equal to this value. So, in summary, for R2, for matrices that transform from R2 to R2, the determinant of M tells me whether matrix is invertible or not, and the determinant of M tells me the new transformed area of the area that was originally between A1 and A2. So it shows the new transformed area of the square area, because it was originally a square. So let's look at this again. This square is now, after multiplying by the matrix M, multiplying every vector inside that square by the matrix M will give me this new area. This new area is equal to the determinant of M. Now this applies as well to matrices that are 3 by 3. So the definition of the determinant of a matrix in M3 is defined as follows. If we have a matrix that's made out of 3 vectors, A, B, and C, 3 horizontal vectors, if we call the vector A, A1, A2, and A3, the vector B, B1, B2, and B3, the vector C, C1, C2, and C3, the determinant of M is defined as the triple product between those 3 vectors. And if you don't remember, triple product at the end of the cross product. So the triple product was defined at the end of the cross product section. And so from that section, if you take a look, the triple product of 3 vectors is equal to 0 if and only if equivalent to the 3 vectors are linearly dependent. They are multiple of each other, which is also equivalent to, if the 3 vectors are linearly dependent, go back to the previous section, look at matrices. If the 3 vectors are linearly dependent, the matrix is not invertible. I can't find its inverse. The determinant of M also has another function, which is to give me the volume of the cube that's originally between or made out of E1, E2, and E3. So the cube made out of E1, E2, and E3, once I multiply M by this cube, I multiply M by each vector. So M E1 gives me vector x1, M E2 gives me vector x2, M E3 gives me vector x3. So I have a new shape. The new shape, it's not a cube anymore, but the volume of the new shape is equal to the determinant of M. So the determinant of M is equal to the new transformed volume of the original cube that is made by the 3 orthonormal basis vectors. Okay, so don't forget those 2 facts. The determinant of M is 0, means that M cannot be inverted, which means the vectors associated with M are linearly dependent. The rows are linearly dependent. If the M is not invertible, we'll remember from the last part, that means that the kernel of M is not just a 0 vector. So there is a vector in R2 or in R3, wherever we're working, R2 or R3. This vector is not 0, yet when the matrix is multiplied by this vector, I get a 0 vector. And the opposite statement, if the determinant of m is not equal to 0, that's equivalent to m is invertible. That means that the factors associated with m are linearly independent, which also means that the kernel of m only has the 0 vector. Now there is another function of the determinant of a matrix in R3, which is the following. If I have three vectors, u, v, and w, their volume, or the volume that's made out of the parallelopiped made out of those three vectors, the volume is equal to the triple product u dot v cross w. If I have a matrix M, the matrix M takes u and gives me mu, takes v and gives me mv, takes w and gives me mw. So I have three new vectors. The new volume is equal to mv dot mu cross mw. The nice thing about the determinant is that it gives me the ratio between the new volume divided by the original volume, which means when we start talking about continuum mechanics and solid mechanics, this carries information on how objects deform and how the volume changes locally when the objects deform. A few properties of the determinant. The determinant of the matrix of the combined action of the matrix and M is equal to the determinant of N multiplied by the determinant of M. The determinant of a number alpha is a real number and M is a matrix. The determinant of alpha M is equal to alpha cubed determinant of M. This is true when M is a 3 by 3 matrix. And the determinant of I, which is the identity matrix, which we haven't really talked about yet, but we all know from previous. The determinant of I is equal to 1, because that's equal to, if I call this E1, E2, E3, it's equal to E1 dot E2 cross E3, which is equal to 1. Or if you look at it as the volume, since if I put here u v w, and if I multiply this by the matrix identity matrix I, IU will give me u, IV will give me v, IW will give me W, and so the new volume will equal to 1. The new volume over the old volume, the ratio of the volumes is equal to 1. Alright, so this is it for the discussion on the determinant of the matrix. The next thing we want to discuss is a few other properties of matrices, the transpose of a matrix, the inverse of a matrix, and finally the eigenvalues and the eigenvectors of a matrix, what all these things mean. So the first is the transpose of a matrix. In the previous courses where you studied the transpose of a matrix, you were given a matrix where with certain rows and the transpose of a matrix was defined as simply take the row and make it a column, and so this becomes the transpose of your matrix. This definition still applies, of course. However, you need to realize that this definition really only applies for Euclidean vector spaces. Of course, we are only working with Euclidean vector spaces here, but in general, the more abstract and the more general definition of the transpose of a matrix is defined as follows. The transpose of the matrix M is the unique matrix that satisfies the following. For every u and v in Rn, mu dot v is equal to u dot m transpose v. And you need to verify that both definitions are equivalent. Now, in many cases, I'm going to use this more abstract definition because it makes the some proofs much easier to utilize this definition without having to resort to components. The inverse of a matrix, we discussed the inverse of a matrix for an extended section, and the measure whether a matrix is invertible or not lies in the determinant of M. But once I know that a matrix is invertible, let's see what a matrix is invertible means. It means if I have a vector here, x, then the matrix M will give me a new vector mx, and then the vector m minus 1, the matrix m minus 1 here, if M is invertible, then there is a matrix M minus 1 which, when multiplied by M, will bring me back to X. So if M is invertible, there exists M minus 1 such that M minus 1 M x is equal to x. That applies what's x. I should have defined x first. There exists M minus 1 such that for every x in Rm, so again I have to properly define the objects that I'm dealing with. If M is a matrix that's n by n, if M is invertible, that means there is another matrix M minus 1 such that any vector x in Rn, when I multiply M minus 1 M by x, I get x again, which means M minus 1 M is equivalent to the identity matrix. And since M is invertible and M minus 1 is invertible, that means M minus 1 is also equal to I. Now, to find the inverse of a matrix, of course, it's better to use a software because it's a very detailed process and a technical process. That's not really the objective. Is not to show you how to find an inverse of a matrix, but quickly, if I have a matrix that is 2 by 2, M is equal to A1, A2, B1, B2, then M minus 1 is equal to 1 divided by the determinant of M multiplied by B2, A1. So basically exchange. What I did is I exchanged those and change the signs of the off-diagonal components. And you can verify M multiplied by M minus 1, verify that this is equal to I, or M minus 1 M, verify that this is equal to I. Of course, any software will give you the inverse of a matrix right away. If M is in a 3 by 3 matrix, where M is equal to A1, A2, A3, then the inverse of M is equal to 1 divided by the determinant of M multiplied by, I'm going to put here 3 vectors. This vector is equal to B cross C. This vector is equal to C cross A. And this vector is equal to A cross B. And you need to verify that M minus Y mine is equal to M minus 1 M equal to the identity matrix. Now the next section in the book is not covered in the course. The next section, and the last section for this part of the lecture, is eigenvalues and eigenvectors. Now, what you are used to from eigenvalues and eigenvectors is that you're used to mx is equal to lambda x, which right now, maybe like this, you might not really see what it means physically, but if you look at it graphically, maybe it will make things a little bit clearer. So let's look at a circle of vectors. And what we know now is that a matrix M will take those vectors and we might change their direction and their length. So we'll take this vector and maybe become longer. And since it's a linear map, the negative of this will also be a negative and we'll have the same length. And maybe take this, make it shorter, and maybe change its direction, and so on. So we end up with this ellipse that's the image of this map after transformation. There is a special vector. I'm going to call this vector x. There could be a special vector x when m is multiplied by x. I'm going to get another vector mx. And what's unique by this image about this image is that mx is parallel to x. mx is parallel to x, or in other words, mx is linearly dependent on x, or mx is equal to a number multiplied by x. And this is the unique thing. It doesn't happen that often. Not every matrix would have a vector that would keep its direction if you multiply that matrix by that. But if it happens, then I call this vector the eigenvector, and I call the multiplier here the eigenvalue. So the proper definition of eigenvalues and eigenvectors is as follows. If I have, I'm going to define it for a general matrix n by n. If I have a square matrix, then lambda, which is a real number, if is an eigenvalue, and we pay very close attention to the definition, then lambda is an eigenvalue if there is a vector in the n-dimensional vector space where this vector is not equal to 0. This is not a 0 vector, otherwise the definition wouldn't work. Then such that mx, the new vector that comes after I multiply m by x, is equal to lambda x. In this case, x is called an eigenvector of m associated with lambda. Now let's discuss how to find the eigenvalues and eigenvectors. To find the eigenvalues or the eigenvectors, I would like to have mx defined. I would like mx minus lambda x, or mx to be equal to lambda x, or mx, this vector, minus the new vector is equal to the 0 vector, which means m minus lambda identity matrix multiplied by the vector x is equal to the 0 vector. Now x from above, the vector x is not equal to 0. Yet m minus lambda I, which is a matrix, multiplied by this vector is equal to the 0 vector, which means that m, this matrix, cannot be inverted, which right away means that the determinant of m minus lambda I is equal to 0. If you solve this equation, to find eigenvalues. So we're going to go now through two examples to maybe strengthen our understanding of the eigenvalues and the eigenvectors. Let's first think, what are the eigenvalues and the eigenvectors of the identity matrix? Now let's see what I does. I, which is equal to 1, 0, 0. What does it do? Well, any x, any vector x in R3, x is equal to x1, x2, x3. What happens when I multiply m by x? Sorry, I by x, this identity matrix by x, I get x again. What does this mean? It means that any vector x is in fact an eigenvector of I. So any vector is an eigenvector because it keeps its direction. Remember, the definition of the eigenvalue or the eigenvector is that when the matrix is multiplied by this vector stays in the same direction. And since when I multiply I by the vector itself, it keeps itself, which means it's in the same direction, and therefore any vector is in fact an eigenvector of I. To find the eigenvalues, just put the determinant of I minus lambda I equals 0, and you're going to find that lambda has to be equal to 1. So the associated eigenvalue is 1. Indeed, Ix is equal to lambda x, and that applies for any x in R3. Now to find the eigenvalues and eigenvectors, usually I'm gonna, if it's an R3 over a matrix that is 3 by 3, I'm gonna ask you to do it using the software. Or if it's an easy one, maybe do it by hand. So it's good to know how to do it by hand. But for the remaining, that's for the exam. But for the assignments and all, you should know how to do it using the software. So we need to find the eigenvalues and the eigenvectors of this matrix. So what's m minus lambda I? I want to make this matrix not invertible. So 1 minus lambda, 0. I'm going to call this matrix, let's say, A. The determinant of A is equal to 1 minus lambda, 2 minus lambda, 3 minus lambda. If I make this 0, therefore lambda equal 1, 2, and 3. These are 3 possible eigenvalues. To find the associated eigenvectors, we use lambda equal 1 first. So I put lambda equal 1, 1 minus lambda, so A, the matrix A, 1 minus 1 is 0, 0, 0, 2 minus 1 is 1, 0, 3 minus 1 is 2. Now I would like to know the x, that when I multiply A by, I'm going to get a 0 vector. What should I put here? It's clear that the vector that I should put here to give me a 0 vector, I can put anything here. I have to put 0 here and I have to put 0 here. So eigenvector 1 is equal to x1, 0, 0. And let's say first eigenvector. So any multiples of this vector are eigenvectors associated with lambda equal to 1. And so all I have to do is I can choose that the first eigenvector to have norm equal 1, which means choose x equal to 1, 0, 0 to be the eigenvector, or 1, of the eigenvectors associated with lambda equal 1. And check in your book, continue for lambda equal 2 and lambda equal 3. And so this is it for the introduction to M2 and M3 matrices. In the next parts, we are going to talk about the special matrices in M2 and M3. In particular, we're going to talk about the matrices that cause rotation and the matrices that cause stretch. And so there are 2 parts left in the linear algebra before the end of the linear algebra part, and these will be covered in the next 2 parts.